Linear equations can always be reduced into the form ax plus b equals 0, which is nice to be able to solve linear equations. And we can show general solutions by just creating sliders out of ax and b. Of course, a is the same thing as the slope, and b, so really I should use m here instead of ax, but it doesn't really matter for the variable. They'll both work the same. So we'll go like negative 10 to 10 as usual in steps of 1. So these give us the solutions. Desmos will automatically understand what you're looking for. This is the solution, right? If you subtract b, then divide by m, you're going to get x equal to um, negative b over m. And you can see we get the exact same line there. This of course, is the solution to this linear equation. But this is the exact same thing as just saying the actual function. So I can either do it like this, mx plus b, and the solution here is when y equals 0, because I changed 0 into y. And this point here has the y coordinate at 0. So it's the exact same thing as just plotting the linear equation, the linear function on the graph and seeing where the x-intercept, which is when y equals 0, is. It's all the same solution. Of course, this can also be written as function notation. So I could use f. I'm going to use L of x here since we're talking about a linear function. And again, it's the same line. I haven't changed anything there. Of course, I can change the slope around and change b around, and that changes where the solutions are. 5.60, well, 5.6 is the solution to this context for this linear equation problem for what we're talking about. But they're all the same solution. Again, the green crosses it, the black line crosses it, the purple line and the red line are the same thing there. They're all just solutions to that problem. So one way we can see this in action is if we actually just look at kind of a random one. I tested this in my own preparation, but I just created a random equation, and you can solve it pretty much the same way I did here. So let me just follow along that one. 46x plus 68 x minus 200 equals So you can see here, I have quite a long expression here, and I can show it all if I just expand this expression window a little bit larger. And let's see if I can find the actual, yeah, there's a solution there. Negative 32, and then some decimal part there. I'm not sure if that's rounded or not, but I can find the exact solution by solving this equation. Now, also what I can do is I can get all this over to one side. So I'm going to write the same thing here. And then I'm going to subtract this portion over to the other side of the equation. So it's going to be copy that over, subtract that portion. And I'm going to add this portion over, and that, of course, is going to equal 0 now since I moved this portion over and I added that portion over. So this is going to equal 0 in this context. And you're going to see it's going to be the exact same line here. This green line overlaps that blue line perfectly because it's the same solution. So I haven't changed anything in this equation. It's still the same equation. But now what I can do is I can actually graph this function here as y. It's gonna be hard to see here because I think it's very steep in its slope. So all I have to do to show that is show large values of x. Sorry, no, I need to show a smaller area of x and then a larger area of y, and that will show you the steepness there. And you can already kind of see it. There we go. So the first two were just vertical lines because those were actual solutions of the equation. and then this one is actually a slanted line there. And I could, if I wanted to, I could actually create the general. I don't have to write y in there. I can just write the expression like this, and Desmos will understand this as a line. And I could find. So b is the y-intercept. It's going to be that line there. So approximately negative 14,952. And then the slope, I can use the slope formula if I wanted to find this equation of the line. So the slope formula is m equals y2 minus y1 all over x2 minus x1. That's the slope there. So one way I could do this is I could actually take this thing here and write this in function notation. So if I did this as L of x, put it in the front there. It got confused with the L of x being in the back of it. It understands y perfectly fine, but the function notation, it likes to be in the front. And now really all I have to do here is L of x is the same thing as y. So I just need to choose two values for x1 and x2. So for instance, I could just choose 1 and 2. And now the y values are the corresponding x values plugged into the function. So all I have to do here is do L of 1 and L of 2. And there we go. That's my slope value. So if I do this, I should say this is the slope. It got confused drawing this graph. If I plug this value into m, you should see that this black line now covers the purple line. Not exactly, since this isn't exact, but we'll do negative 462. There we go. And so it looks like the black line covers the purple line perfectly fine there. Now, instead of doing that, right, that was a bit of work. What we could do is just solve this this expression here, or I should say the equation, and we can get the solution exactly to be this thing here. And all of this can be done on Desmos because this is all a calculator here, which makes it easy to see to double check that you actually have the work correctly. So for that, I'm just going to grab this one and simplify the expression down. So I need to simplify the left-hand side. Really for that, I need to distribute the 68. 68 times x is easy, that's just 68x, but 68 times 200 is a little bit more confusing. So let's do 68 times 200. It is negative 200, so it's going to be negative 3600 there. So we're going to have negative 46x plus 68x minus 13600. Okay, now on the right-hand side, I need to do 0.687 times 65. Again, I can just use the calculator here. 687 times 65 be 44.655x, since there's an x in this part here. And now I need to do negative 687 times 7890. So I just need 7890. Okay, that's going to be plus 5420.43. And then the minus 4068 is still tacked on there on the end. Okay, so now I can simplify this further by combining these two x values and then these two constants. So that, right, I can just do negative 486 plus 68. So we know it's going to be negative 418x, then minus 13600 equals. I should also note here, I'm going to turn off these two here, that I know my equations are the exact same because these vertical lines are overlapping. As long as they overlap each other, then I haven't changed the equation. I haven't made a mistake in my algebra. So that's a great way to double check your work if you're doing this by hand. Okay, now we're going to get the 44.655x. Nothing combines with that. But now we can add these two values together. I can just copy that, paste it. Okay, it's plus 1352.43. Once again, this vertical line here is overlapping the other two, so I know I haven't changed anything there. And now I can get it all over. I can get the x's to one side and the constants to the other side. I can subtract this value to this side. So when I get negative 418 minus 44.655, negative 462.655x equals, and now I'm going to add this value to this side. So it's going to be this plus this, since I'm adding it over to that side. And I get 14952.43. Once again, it's overlapping the rest of the lines, so I know I haven't changed anything. And again, we should be expecting this value as the result. The last step is, of course, just to divide out this number here. So we're going to get x equals 14952.43 divided by negative 462.655. And there we go. Negative 32.31875 is a rounded number. It's actually this, and I'm guessing that it's going to be much longer than that, but that's where we're at there with the solution. I've done it all correctly, and that's the actual value that we get. So in this process, I used decimal numbers and whole numbers. Desmos understands fractions perfectly fine, so we can also do a fractional one. So for that, I'm going to go back to home and delete this stuff and restart with a fraction version instead. So the function or the equation I'm going to use now is, again, I just created this randomly in testing, and it worked well. 23 over 8, 7 over 9. Oops. 20 minus. Okay. So you can see here, the slope is still confusing what we're talking about, but this is the equation here. I can subtract this stuff over to the other side. Let me copy that over and make this a minus. And that is the function. This would be, of course, equal to 0. You see we get the same thing, but if we just make it equal to y, that's the function itself. If I wanted to, I could try and get the line here. I know that would be my intercept, so I'll just do negative 12 for the estimate. And then the slope, let's see if I can just drag the slider. Turn on the function here. Okay. And something like 6, it's between 6 and 7. So I'm just trying to match up the blue line here. I'll turn off this red one. Just trying to match up the blue line. So 6.5. Close. 5.5, maybe too far. 4. Oh, the discrepancy might actually be coming from the intercepts here. Let me actually do that value. Well, you get the idea. We're just trying to look up the slope, and this is kind of an estimate for what the actual solution would be, right? We could calculate the slope is what we wanted to do, whatever. But there's no need to do that since we have the actual value. Desmos finds the value of the solution that we want, and we can prove that true by doing the algebra itself. So for the algebra, we just need to get x by itself, and that gives us the solution. So for this, right, I can distribute the 7/9 into there. 7/9 times 20, really all I have to do for that. Let me flip this around. For that, I just need to do 7 times 20, which is 140. This first part's going to be the same. But now we have equal to 140 over 9, since 20 is the same thing as 20 over 1, right? Now we have 7/9 times 9/4. The 9's cancel and we get 7/4, and then x. Once again, we have the same vertical line there, so I know I've done everything correctly. Now I can add the x to one side and subtract this to this side. I'm going to add this over and subtract this over. So we're going to get, I'm adding the 7/4 x over, so I can remove that now. And now I'm going to subtract the 23 over 8 over. So I can delete that now. And we still have that same vertical line there, so I know I've done it correctly. Now I can combine the like terms. So these are like terms here. I need to have common denominators. 135 is divisible by 5. Yeah, 5 and 27. 27 is just 3 times 3 times 3. So 4 doesn't have any common factors between 135. So the least common denominator is going to be 135 times 4. In other words, I need to multiply this first fraction by 4 over 4, and this one by 135 over 135. So doing that, I'm going to get, we do 674 times 4, and then 7 times 135. Okay, so 674 times 4 is 2696. Oh, oops. 2696 over 135 times 4 is 540, as I have down here in this first spot. And then plus, I'm going to get this one to be the same thing. I should put the x on there. 7 times 135 is 945. And then 4 times 135, we already found that here, is 540. And then x. And the least common denominator here is going to be 9 times 8. So I have to do, which is 72, 140 times 8, and 23 times 9. So 140 times 8, 23 times 9. Okay, and now I can finish that. 140 times 8 is 1120 over 72. Minus 23 times 9 is 207 over 72. Once again, the exact same line. I haven't changed anything. I haven't done any incorrect. I actually deleted that. Any incorrect algebra here. It's all been correct. Okay, now I can actually combine these two things because I have common denominators on both of these. So I can just do 2696 plus 945. Gonna have x equals, and then here we have 1120 minus 207. And that's going to be 913 over 72. Again, same vertical line. Okay, last step is to multiply this thing over there. It's the same thing as multiplying by the reciprocal, or I should say dividing and then multiplying by the reciprocal. So x equals 913 over 72 times the reciprocal is 540 over 3641. And there we go. We do indeed have that same solution all the way in the back. 1.88066. Well, this is the actual solution. I could, of course, combine these. I could reduce the 540 and the 72 for sure. But there's not really any need to, since Desmos gives me the calculation right there. So that's the exact, well, this is the exact solution. This is probably an approximation to this place here, but it's all found on the graph right there. So a system of equations or inequalities is where we try to find a solution with different constraints. Here we're going to be looking at systems of equations, specifically linear equations. And in general, a system of linear equations is going to have two linear equations. So I could do y equals ax plus b, and then y equals cx plus d, and then create all those sliders. And in general, we're going to have three types of solutions. We're going to have the main solution is going to be something like this, where the two lines intersect, and the intersecting point is the solution. Our system of two linear equations is designed to be the case where we're interested in the intersection point, and that tells a lot about whatever the context of the problem is in. So this is kind of what we want, because it gives us an exact solution that we're looking for. But there are two other types of solutions, namely when the slope is the same, in other words, the number multiplying the x, so 3.6 here. These are the same slope, 3.6 and 3.6, and that means these two lines never intersect. They go infinitely upward and infinitely downward, and they never intersect. If it's slightly off of this, right, if I do 3.5999, even like it looks like it's parallel, but in fact it is not. At some point the two lines will intersect. I'm not sure where. Maybe down here or something like that, but it's a little bit easier to see if it's not so dramatically different. 3.58. If I zoom out a little bit and go down, Desmos will actually find the solution right here. That's where the two lines intersect. So yeah, it's gonna be too hard to see exactly where it's at, but the two lines do cross, and you can see that with the point that Desmos found. So that's the first type of solution. That's not what we want. The intersection is what we want, but the two parallel lines, when they're the same slope, means they'll never intersect, and there's no solution. The other type of point is kind of a trivial one, and that's where the two lines are actually the exact same line. So here we have the same slope, A and C are the same, and B and D are the same. And so these two lines intersect at infinitely many points. Every single point on the line is where the 2 points, the two lines intersect. And so this tends to be not an interesting solution. It actually creates some issues in some contexts of linear algebra. But in general, we're looking for the point of intersection between the two lines, and that's what we're going to be looking at further on here. So in my testing, I just made some random equations here. 6506, and then negative 98x plus. My goal was to kind of model something that was something that you kind of more see in a real life scenario. In this case, what you're going to see here, I believe, it's going to be in quadrant 1. Yeah, but both of the equations are going to be in quadrant 1, and the point of intersection is going to be as well. So let me change the bounds here so it's a little bit easier to see. I'm going to go from 0 in quadrant 1 up to 700. So that's where both the lines are. And then I'm going to just start adding zeros onto the y-axis to see where we're at for that. So 1, 0, 0, 0. Okay, there we go. So this is in quadrant 1 here, and the point of intersection there is that point right there. So the x value is 9.64442, probably rounded. And the y value is 59,731. This is probably going to be like a dollar value in a lot of contexts. So you do 59,731 and 85 cents if you round up. Okay, so to actually find this solution, all we have to do is set these two things equal to each other. And right there, we see that Desmos finds the solution at that x value, because this is just a linear equation. There is more context to this problem, so that the actual thing we want to know is not just the x value, but also the y value. However, it's easy to find the y value once you know an x value, since all you have to do is just take this number and plug it into either one of these two things, because it's going to be the same. The point of intersection is where both of the expressions give you the same value when you plug in the same x value. So we could do that, right? If we just take that point and then copy it into here. And there we go. We have this y value approximately. You can see that it's not quite the same because this was an approximation. To find the exact solution, we have to solve this linear equation, which isn't too difficult because of the form that it's in. So for that, let me go back to x here. For that, all I need to do is just add this number over to this side and then add this number over to that side. So I'm going to get this plus 98x equals, I'm going to get this plus this number. As you can see, once again, we're still on that same line, that same black line. It's kind of hard to see, I guess, with those. But the black and green, blue lines overlap, so I haven't changed anything there. Now I can combine the two expressions, 6868 plus 98. And then 6677 plus 6506. Once again, green, blue, and black all overlap here, so I know I haven't changed anything. We still get the same solution point there. And finally, of course, we're just going to do x equal to 67183 divided by 6966. And there's the exact solution for that system of equations. And this is going to be exact. Of course, this is going to be an approximation still, but that is how you can solve systems with Desmos. For systems of inequalities, we're going to first look at the one-dimensional case, because that's what basic linear inequalities are. They're really just one-dimensional things, and we're going to look at how it affects the x-axis and the points on the x-axis. So for that, let's go remove the grid and the y-axis. Here we are back with the x-axis. So now let's consider basic linear inequalities. So any linear equation can be reduced down to the form ax plus b. And now we're looking at an inequality, not an equation. Still the same kind of process applies, but now we have to consider greater than y or less than y, or greater than or equal to or less than or equal to. And again, we're not concerning ourselves. Let me change this to a tad bit brighter. Yeah. We're not concerned with the y values. We're only really concerned with the x values. So in this case, what we have here is, if you simplify this down, we have x plus 1 is greater than y. And really, we're only considering the x values here. So when that equals 0, we're on this point here. As usual, right? When y equals 0, that's what we're kind of looking at, is this point here. And that means that the solution is going to be all the values that are greater than 1, greater than -1 here. That's what this point is. And that we can see if we just subtract 1 to the other side. This is the same thing as x greater than -1, which again is the exact same value there. So that's the solution set. X greater than 1, that's of course, you can graph with a parenthesis there and then an arrow going on that way. We can also graph it with interval notation saying -1 comma infinity, which, the infinity symbol is not I don't believe it's anywhere on here. So I'm just typing infinity there, not as a variable, but that's the solution set for this linear inequality. Of course, as we change the values of a and b, the actual solution changes as well, right? If I change a, you can see that if I change a to this, then I'm actually, in this case, all the values of x are a solution, and that's not really a great case because a is 0 here and x just goes away. So that's like saying is 1 greater than 0, right? A is 0, so x goes away, b is 1, and we're only looking for the values where y equals to 0. So this is always true. It's trivially true. So we're really not interested in cases when a is 0. It's really the rest of the cases that we're curious about. So right, when a is negative and b is like this, then we can see that here x has to be less than this value here. Again, it's less than because we have a strict inequality here, the less than symbol, and we have a dotted line here. Again, we're only considering the x values for this point, even though this is a slanted line in the x and y space. We're only concerned with the x values of the solution. So that's what the x-axis shows us. So yeah, you can try out different things as you see fit, and that'll give you different stuff. Of course, if you go from greater than or to greater than or equal to, then all that happens is that this dashed line becomes solid, and now this point is included in the space. So in this case, the solution here would be, right, it'd be ax plus b equals 0. In this case, it would actually be, I should just type the numbers in, 3x minus 7.1 equals 0. I add the 7.1 and divide by 3. I get x equal to 7.1 divided by 3. And that's that point right there. And x is all the values greater than, since that's the side that's shaded in. So the solution set would be 7.1 over 3. I'm just using this because that's the exact solution, and then comma infinity as it goes on up to positive infinity. And we're using a parenthesis there since Desmos doesn't understand the bracket parenthesis notation. But you get the bracket because it includes that point, and the parenthesis because infinity can never include that point. Okay, so that's the basics of linear inequalities. Of course, you can simplify inequality down to this point here. Make sure when you're simplifying it down, right, if you have something like this, let's do negative 3.81 x plus, just make up some numbers there. Or no, wait, I want to do this. Like this. That when you simplify this down, or any such case like this, where we have to divide or multiply by a negative, division is the same thing as multiplication in mathematics, just by the reciprocal. Whenever you do that, you need to flip the inequality. So in this case, the solution is going to be x is less than 6514 divided by negative 3.81. I flipped the inequality so that the when I divided by that negative, I flipped the inequality there. So this is the correct solution, and we can see that if we zoom out enough, let me turn off this stuff. Zoom out enough, we can find that solution set. There it is. And I turn that off, and you can see that it's the exact same solution. And that, again, it's only the case if you flip the inequality. If I didn't flip the inequality, then you see that the two different sides are shaded, and that means you did it incorrectly. So that's the key thing to keep in mind when working with inequalities versus equations. Okay, so now let's consider two-dimensional space now instead of the one-dimensional space. So let's add this back in, and now we can consider the actual full solution set here, not just the x-axis. We're also considering the y values as well. So for this, right, when we have this equation here, the boundary line is going to be the equation where it's equal to. That's always the case. So, and then of course, that's just this line here, the linear function there that's defined by those slope and intercept. So if I do this, that means the solution set is going to be, because it's not a restricted inequality, that means we do include the points on the line, but also all of these points there. Well, we can test points to actually see, to determine if it's true or not. And we could have done the same thing in the one-dimensional case, and I'll go back and check that really quick. But we can test points like, for instance, 0, 0. 0, 0 is a point that's very easy to test because zeros are easy to plug in and simplify. And this is inside the red line. So that means that if I test 0, 0, I should get a true statement. And 0, 0 is the same thing as 0 for x. That means we have negative 3 times 0. B is 5.4 in this case, and then greater than or equal to y is 0 as well, since we're testing 0, 0. I don't actually want to plot this because I'm just testing. Sorry, this was 0 here, not x. So simplifying the statement down, right? Negative 3 times 0 is just 0. We get 5.4 greater than or equal to 0. And that, of course, is a true statement. So I tested 0, 0. Let me plot that point in there. Let me do an expression here. Test 0, 0. Let me just plot that point. So I tested 0, 0. I plugged into the equation that we get from this resulting A and B, and then I get a true statement. So that passes the test. Another point we can test is something like way over here. Let's test this point here. This is negative 6, 10. So let's test negative 6, 10. Okay, there's that point. And this should be a true statement as well, since it's in the solution region that that Desmos is showing. So if we test that, we're going to get A is negative 3, X is negative 6. Then we got plus 5.4 greater than or equal to Y is 10 in this case. And so now all you need to do is just simplify the statement down. Negative 3 times 6 times negative 6 is positive 18 plus 5.4 greater than or equal to 10. And hopefully you can see right now, yes, this passes. This is 23.4 greater than or equal to 10. And yes, that is a true statement. Of course, if I test a point that's not in this side, at that point over here, then we know that it's going to be result in a false statement. Now, I would always recommend testing points that are on the axes, because in that case, either X or Y is 0. The best points to test are really the ones where X is 0, since A times 0 is just 0. And you just have really a number to check there. But you can test any of these points. Let's test the simple one, and then one that's a little bit more complex. So in this case, let's test 4, 0. And I'm not going to write the expression there, but let's just type it's 4, 0. So I'm testing this point. It's not in the space, the solution space, so it should not be a valid solution. If I type it in there, I get it's negative 3 times 4. See, plus 5.4 greater than or equal to 0 is Y is 0 in this case, and that of course gives us negative 12 plus 5.4, which is just that would be negative 6.6 greater than or equal to 0, which is a false statement. Negative 6.6 is less than 0, so that is why it's not in the solution set. Of course, I can test any of these points. I really want to. One thing I should test really quick, though, is this point here, a point on the line. And let's test a weirder point, like something up here. So negative 0.41, 4.17. That looks to be exact, since it's only 2 places, and I think Desmos rounds the 3 places, so it might not be exact though. Okay, this point looks exact. 0.4, 4.2. Let's test that point. 0.4, 4.2. That looks to be on the line, and since this is not a strict inequality, this point should pass the test because it is on the line. And let's see, so we can actually see if this is an exact point or not. So let's plug it in and check. Negative 3 times x is 0.4 plus 5.4 greater than or equal to y, which is 4.2. So negative 3 times 0.4 is negative 1.2 plus 5.4 greater than or equal to 4.2. And that, of course, gives us 4.2 is greater than or equal to 4.2. And that is a true statement. 4.2 is greater than or equal to. Since it's equal to, it's a true statement, and it passes the test. So this point is in the solution space. Of course, if we change this to be a non-strict inequality, so I just hit backspace there, now you can see it's a dotted line, and down here, this would end up being a strict inequality for all these cases. And 4.2 is not greater than 4.2. So that would be a false statement, which is why, again, why the line goes from dashed to solid to designate that difference there. So again, if we go back to the two-dimensional case, where we're just concerning ourselves with the x-axis, you can see that right, this point here still satisfies this because it is in the feasible region, or I should say the solution space, which is shaded in, and this point does not. It's still the exact same application applies, right? Whenever the shaded region covers a part of the points, or in this case on the line, those are all valid solutions. So all of these points here are in the solution space, and these ones are not in the solution space. All right, a question you might have is, what happens if we have multiple linear inequalities? So we talked about systems of linear equations. What about systems of linear inequalities? How does that change what we're looking at? Well, let me remove a bunch of these things here and just clean up the space what I'm looking at. And let's look at a second linear inequality. In this case, I'm going to do less than or equal to y, just to have something different than the first one. And this is what we get. Let me color it blue. Okay, and so now if I kind of do, you know, different stuff here, this is what I get. And so again, the solution is in the space that's shaded. Well, if we're saying that these two equations, or I should say inequalities, if these two inequalities are talking about the solution, both of them are a part of the solution set, then that means the solution space that we're talking about has to be where it satisfies both of these inequalities. And that, of course, is going to be in the overlap, which is this region here. It's not going to be just this region, right? The points in this region are going to satisfy this equation, but not this one, since none of these points are shaded in the red. And then, you know, vice versa, the points in this region are going to satisfy this equation, but not this one. And of course, all of these points satisfy neither. So this is the only space here that we are concerned with. This is actually called the feasible region. All the feasible solutions are in this region here. And so there's no real distinction between y only 2, right? We can have as many as we want, right? We could do, let's see, so mx plus n is greater than or equal to y. And here, right, let's do something like this. And so now you can see that the only overlap between all three of these, right? If I turn off these two, you can see that this side is shaded in. And then if I turn on this one, I know that I'm only in this strip here that continues on indefinitely upward. It's like a triangle that continues indefinitely that way. But if I add this one in here, then we can see that really the only piece that's feasible is in this triangle right here. This like very thin strip of triangle. So this is the feasible region. Everything we're going to be considering for our solution set has to be in this region. And of course, there are infinitely many points in there. But that's where we have to look. We can ignore everything else around here. And of course, if you just change this around slightly, you can get, you know, different. This one's kind of nice because the triangle's a little bit clearer, but that would be the feasible region in that one. And of course, we can add in another set. Let's do. So in this case, right, with the basic thing there, now we're in this feasible region here. and that's the only one that satisfies all 4 of these inequalities. Now, typically in a context when you're using these types of things, you're going to actually have other kind of constraints, not just these constraints here. So let me actually get rid of a couple of these and just go down to 2. Other constraints would be something like bounds on the values you're talking about. So in this case, like x greater than or equal to 0, and y greater than or equal to 0. Or in other words, we're in the first quadrant. So you really don't need these bounds showing. All you have to really consider is just being in the first quadrant. And if that's the case, then only this triangle is, or sorry, it's a quadrilateral that has 4 sides. Only this quadrilateral is the feasible region for this system of linear inequalities. And then from there, you can have further inequalities that might cut the space up more. Let's add back in one of them, mx plus n. So, for instance, like I guess you could do something like this, where this actually further cuts it down into this piece here. So like this would be like a hard cap if I were to do. Actually, let's do this. Let's say something like this, where x is less than 6. So in this case, we're saying x is hard capped at 6. It's greater than 0, but less than 6. So it's actually bounded between these 2 things. And I can actually show that here at all in one. If I do 0 is less than or equal to x, which is less than 6, then this creates that bounded region. And now we're only in this space here because, again, y has to be positive. And so we're only in this small region here. So that's how linear inequalities, really any inequality, but linear in this case, can cut up a region of solutions. And what you're looking for is the overlap. Of course, it's very easy to do with a graphing software like Desmos, to see where the region of overlap is. To do it by hand, you'd have to do a lot more analysis on looking at where these, what kinds of points would satisfy all the things. But in general, like for actual applications of this, you're actually going to have extremely complicated, like extremely long linear inequalities. Not just ax plus b, but something more like ax plus by plus cz plus, and then maybe a bunch more variables in there, but they're all linear in that they're just x, y, z, not x squared or something like that. And you can't graph them. You have to use software and other techniques like linear algebra, that you want to learn linear algebra, to solve a solution set like that. But this is the basic idea of it. And then in all these cases, what we really are looking for is the feasible region, the solution in the feasible region for an objective function. So the objective function is the key thing here. That is what we're looking for. And typically, an objective function is something like I want the highest profit in the feasible region, or I want the lowest cost in the feasible region. Those are like the easiest, like low-hanging fruit for that objective function. And that typically is something with like a z equals and then some statement, at least in this context, since we have x and y. The issue is that we're actually adding in a third variable. And so the way we would do this is we have to graph it in 3 dimensions, but we're not really doing that here. And so a way we can get around that is we just show different, like, it's like a topological graph of like a map. We're going to show different lines that show different levels of the z. So for instance, let's just type something in there, like 3x plus 2y. This is our objective function, and the way we can show this on the graph is by creating different values for z and then plotting the corresponding lines. So how I'm going to do this is going to be a little bit weird, but I'm going to create a list of values. So I'm going to call these levels. Again, if you've seen a map diagram of like the topological space of like mountains and everything like that, you see like rings and things on there showing equal elevation spots on the graph. This is a very similar idea in that we're talking about levels of the objective function. In this case, so I'm just going to create levels. I'm just going to create a list, and it's going to be 0, 1, 2, on up to 100, because I'm not sure how many I need. And then I'm going to create our objective function is 3x plus 2y, and I'm going to make it equal to levels. And what you see here is topographical level lines. So each line shows a different quote-unquote elevation of the objective function. And in this case, I think it's going to be helpful to think about this as profit, and we're trying to maximize the profit. So this would be the minimum profit because it hits 0, 0. The next level up is going to be this one here, and then this one and this one. And for our context, let's just say that what we want is we want the highest level possible. So like the highest revenue is the idea there. And that, of course, is going to be inside the feasible region. Well, this is the feasible region. So all solutions that we want are going to have to be in here. And the highest region is going to be at this vertex point. That's the highest level line here of all the level lines in the feasible region that crosses. Now, technically, it's not going to be this point because that point's not allowed. But we can go slightly in from that vertex point. The vertex tells us the vertex is just where the lines cross. Where the solution would be, there's a theorem in mathematics that says every solution for this kind of problem will be on one of the vertices of the feasible region. So it's going to be this one here, somewhere around there, this 0, 0 point, and this one right here. So it's going to be those four that are the key ones to look at. And of course, in this case, this is one we're looking at. Now, since the constraints are strict inequalities there, then we're going to look really, we're going to probably have to use some analysis and like what actually makes sense in the context. Something just slightly inside here, somewhere around this point, that's going to be our maximum profit in this case, if that makes sense.